Again, it's a red stick.
What is going on, guys? Welcome to the fourth episode of the Algorithms and Data Structures tutorial series. In today's episode, we're going to talk about runtime complexity. So runtime complexity is essentially what we're interested in when we look at an algorithm. And for this, we're going to have to go deeper into theory and also a little bit into mathematics, because now we're getting into the real analysis of algorithms. And this analysis, or analyzing algorithms in general, is something that can be done from multiple different perspectives. It's not just one thing. You cannot just say I'm analyzing an algorithm for its efficiency if you don't define what you mean by efficiency. So in today's video, we're going to define a lot of terms. We're going to define what efficiency is, runtime complexity is, and we're going to take a look at the framework that we're operating in here. So let us get right into it. So let's start by talking about efficiency, because efficiency is a very vague term and it's constantly used when it comes to algorithms. For example, if we analyze an algorithm, we always want to know, is this efficient? When we analyze two algorithms, we want to know which one is more efficient, but we need to define efficiency in the first place. What does that mean? Because everyone can define different metrics for efficiency. So for example, one possible metric would be the memory space. It might not be the first thing that comes to mind, but the memory space is definitely something that's important. Let's say we solve a problem in 10 seconds. This is just an imaginary example here, but we solve a problem in 10 seconds, but it takes 10 terabytes of space to solve the problem for some reason. Then we have another algorithm that solves the problem in 10 minutes and only takes 20 gigabytes. If this is the algorithm, or these are the two algorithms, if you look at speed, you're going to pick the 10-second algorithm. If you're going to look at space, you're going to pick the 20 gigabyte algorithm here. So it is important what kind of metric you choose, because another metric, of course, would be the runtime, which is essentially the time it takes to solve a problem, to finish a task. In this case, this one would win, but if we look at memory space, this one would win. Also, you can add some additional metrics, like, for example, problem-specific metrics. If you're solving the problem of sorting a list, you could say the number of comparisons, for example, number of comparisons made, or number of swaps. So for example, you could say when you're dealing with sorting algorithms, you could say, okay, I really don't care about the number of comparisons. I'm not going to talk about that when I talk about efficiency, but I really care about the number of swaps I did. So if I compare numbers, it doesn't matter, but if I swap them, this is an operation that I want to look at. It doesn't make sense, but you could do that. So the metric for efficiency is whatever you define it to be. In this tutorial series, we're mainly going to look at runtime as a metric. We're going to look at runtime complexity in particular, because this is what we're going to define in this video even further. But as you're going to see, runtime is also a very vague term in the beginning. Now, because of that, let us talk about the question of what runtime actually is. And let's go ahead with the naive understanding of runtime is just the amount of time units, seconds, minutes, whatever it takes to solve a problem using an algorithm. And essentially, this definition is not wrong, but it's not the one that we're going to use for this tutorial series, because it will get us into some problems, and we're going to look at what these problems are. Let's say, for example, we have a computer A here, and we have a computer B here, and then we have an algorithm X that solves a problem in 10 seconds, and then we have the algorithm Y that solves the problem in, 2 minutes, which is essentially just 120 seconds. Now, looking at this and looking at the definition of runtime that we just defined, is X actually faster or more efficient than Y? Yes, of course it is, because what do we have here? We have 10 seconds of runtime and we have 120 seconds of runtime. And I think you can see that this is a problem here, because we're running two different algorithms on the same problem, but on two different machines, and we don't know anything about these machines. For example, B could be a machine of the year, 1990, for example, and A could be a machine from 2020, and it could have very high-end hardware, and it could be a very, very efficient machine, whereas B is a very old and laggy computer. So what would be a method to counteract this? Well, you could just go ahead and run algorithm Y on machine A as well. So you essentially run both algorithms on the same machine instead of using two different machines. So what you could do is you could just go ahead and say X runs on A in 10 seconds, or solves the problem in 10 seconds, and Y solves the problem in, I don't know, 8 seconds. Now you can see, okay, Y is better or more efficient than X, but is this true as well? Because sometimes this might be the case. These numbers are not that different. 8 seconds, 10 seconds, it's not that much of a difference. So what happens if at another point of time, X takes 9 seconds and Y takes 10 seconds? Could happen. But the question is, like, how can we determine if that is if X is more efficient than Y, or if Y is more efficient than X? How can we determine that? And also, even if it was possible to do this at the same machine, what would that mean? Would that mean if I want to compare my algorithm here in Austria with your algorithm in the US or in the UK or anywhere in the world, would we have to go to the same computer to execute the algorithm to see how long it takes? Of course not, because that would be unrealistic. We cannot have one central computer where everyone goes to measure how long their algorithm takes to solve a problem. And besides that, of course, we have multiple different factors outside of our control, outside of the algorithm's control, outside of anything to do with the algorithm, that are going to influence the runtime. So for example, in one time period, your computer might lag a little bit, it might have certain tasks in the background, or multiple different factors are going to influence your runtime by 2 seconds, maybe by 2 minutes, depending on what you're doing, what algorithm you're using. So it's not realistic to use actual hardware to determine the runtime complexity or the runtime in general. So what we do is we assume a certain model, a simplified model of a computer, and this model contains 3 steps here, or 3 pillars, principles here that we're going to use here. And I'm going to explain to you why these are important. You don't have to memorize them. You just need to know why we're doing that. And the first point is we have a single CPU, a single processor, which essentially just means we don't care about multi-processing, multi-threading. We're not going to take that into account. We're just going to work with one CPU and nothing more, nothing less. This is just important so that you don't come up with the ideas, but hey, I can process multiple things in the same second, in the same time unit. This is not going to happen here. Second thing is all the data, information, whatever we do with our algorithm is going to be in the RAM, in the random access memory, which essentially means that we have a very fast access. We don't need to go into the hard drive and look for files in the system. All the data we use with our algorithms in this model is going to be in the RAM. And third, and last but not least, is going to be every access is going to take the same amount of time. So it doesn't matter if you're accessing the dataset A or the dataset B, it's going to take the same amount of access time, because we're not going to limit ourselves to hardware stuff. We're going to work on a very high level here, on a very abstract level. We're going to look at the efficiency of the logic of the algorithms. We're not going to waste our time with some hardware stuff, like maybe if we're accessing this part of the RAM, if we're accessing this part of the memory here, we're going to take a little bit longer. We're not going to care about that. We're going to care about the algorithmic logic and how efficient it is. So this is the problem. This is the model that we're going to work with in this tutorial series. Now we have a model and a framework to work with, but we still don't know what runtime actually is. We still haven't defined that yet. And in order to do that, we're going to introduce something called primitive operations. Primitive operations. And these are essentially operations that all take, if we don't define it differently, one time unit. This time unit can be whatever you want. It can be seconds, minutes, whatever it is. But all these primitive operations are going to take one time unit unless we define something else. And primitive operations are everything like assigning a value to a variable like that. So a equals 10, or if you want to write it like that, a equals 10. This is a primitive operation and takes 1 unit of time. Same goes for every kind of addition. So a equals 10 plus b, if we have b defined already, is also 1 unit of time. Now in hardware, in a low level, it would make a difference. It's not always the same. Assigning a value to another or assigning a value to a variable would take less time than assigning the result of an addition. But in this case, we define primitive operations as all these easy things to do, like adding, or also logical operators like A and B, logical and B. Anything that's a primitive operation takes 1 unit of time. Also, every kind of comparison. So if I say if A is greater than 10, then, and then I open a block and do something, this line here takes 1 unit of time. Okay, so these are the primitive operations and they all take 1 unit of time. And now the runtime is nothing but the amount of primitive operations needed to solve a problem. So this is, maybe we're going to write that down. It's the amount of, and I'm not going to write it out, the amount of primitive operations needed to solve a problem. That's what it is essentially, with a particular algorithm, of course, so not in general, but the runtime of an algorithm is the amount of primitive operations needed to solve a problem. This is what we're going to look at. We're not caring about seconds because that is always going to be the same. If you have a computer that processes 1 primitive operation per hour, not going to see that, but if you have such a computer, even if it takes 10 hours, it's still 10 primitive operations that were executed. If you have a very fast computer, you might do this in 1 second or in half a second, in a millisecond, whatever it is, but you still have 10 primitive operations. So the runtime doesn't depend on the hardware, it only depends on how many things do I need to do. And why do we even need to call it primitive operations? Are there any operations that are not primitive? Are there operations that take more than 1 unit of time? And yes, they are, because we talked about pseudocode already. In pseudocode, I can write whatever I want. So I can say I have a list here, and the list is, or contains a couple of values here. And then what I can do is I can just write sort list, or sort the list. I can just make a statement like sort list, and I don't even have to define sort. I don't have to write a sort function down here that takes a list and does something. I can just write sort list, and I can say, okay, I'm using merge sort for this, and we're going to talk about sorting algorithms in a future episode, but I can use merge sort for that. It's not a problem. And if I know, okay, the runtime complexity of merge sort is n log n, I can say, okay, this line takes such and such, or so and so many primitive operations, but essentially I can write lines that have way more, or need way more steps in primitive operations than just 1 or 2 or 3. And this is why it's important, because if I have a line like this, I have a certain runtime complexity in that line itself. Whereas if I have something like creating a list and comparing values, adding values, increasing values, assigning values, it's all primitive. These are all primitive operations, but something like sort the list or find the minimum spanning tree of a graph, I can just write that out in words, but it is not a primitive operation. It's a whole procedure. It's an algorithm in and of itself. So sorting is an algorithm here, and it's not a primitive operation. This is why it's important, and that is what we're looking at. We're looking at the amount of primitive operations needed to solve a problem with a particular algorithm. Now we finally know what runtime is and what we're looking for, but there's still more problems that we can encounter here. And I'm going to show you what I mean by showing you some pseudocode. So we're now going to analyze the runtime of an algorithm here. And it's going to be a very simple one. It's not really an algorithm that solves the problem. It's just code that does something, but we're going to try to determine how many primitive operation this code executes. So now we're going to look at a practical example here. Let's say we start with a list, and this list is a list of some numbers in here. We're not going to statically define it. It's just a list of numbers. And inside of this list, we have some elements, and we could say we have n elements, an amount of n elements. And what we could now do is we could go ahead and also define a variable a, and this is 0. And then we're going to run a for loop that says for each element in list, we're going to do two primitive operations. So for example, we could say a equals a plus 1, and we can say print some message here. Now let's assume that all these are primitive operations. So this is a primitive operation, one primitive operation. Actually, this means first one primitive operation. This is one primitive operation. We're just assigning 0 to a variable. This is a primitive operation. And this, we could also say, is a primitive operation. So essentially, we have 4 primitive operations here. And this loop, obviously, if we have n elements and we iterate through the whole list, so we go for each element once, this loop is going to run n times. And essentially, what you have is you have 2 primitive operations here, 2 primitive operations, plus n times 2 primitive operations, because you run this loop n times and you always have 2 primitive operations in here. So essentially you would end up with a runtime here of 2 plus 2n, which is just the amount of primitive operations of this algorithm. Now, so far so good. It's very simple to understand. You just create a list, you have a counter, you increase this counter for each element, and then you print a message every time, whatever it is. It's very simple, and you always have the same amount of primitive operations. Of course, independence of n, it's not a constant number. Depending on the amount of elements, you have a different amount of operations. But now we're going to add a twist here. Actually, let's just keep these things here, but let's just remove this part of the code here, because we're going to add something to this loop here. And this is an if statement. We're going to say if the element that we're currently looking at, if this element is odd, or let's say if it's even, if this number is even, then we're going to, and you can write it like that. It's pseudocode. So essentially what this means is you're trying to find out with the modulus operator if the number is divisible by 2 without remainder. But you can write it like that. If element is even, you're just going to say a equals a plus 1 and then print the message. So the same code that we just had, but inside this if statement here. And this is again one primitive operation. This is one primitive operation. And now the checking here, if the element is even, is also a primitive operation. This loop still runs n times. And now things are getting a little bit more complex, because we're creating a list here and we don't know the elements here. The elements are going to be different every time. So maybe we have a list full of even values, maybe we have a list full of odd values, or we have a mix of the two. So the problem is, now these two steps are obviously two primitive operations, so we can write that down, two primitive operations. But then we also have this loop n times, and of course you're going to check every time, so you definitely have n times this line, because you're going to say, you're going to always do the if statement. You're always going to check if the element is even. So you definitely have n primitive operations at least. But how many times are you going to enter the if block? And you don't know that in advance, because maybe all the elements are even. So in this case, you would enter it every single time and you would have essentially 3n. So if all the elements are even, you would have 3n, because you would run n times in 3 primitive operations. Or if none of them is even, you would only have n, because of course you will check every time, but these two lines are never going to get executed. So there are differences. It's not always the same amount of primitive operations. It's not always the same runtime for an algorithm. And this is why we have a distinction here, or 3 cases that we want to distinguish. And these are the best case, the average case, and the worst case. So the best case is essentially the case with the lowest runtime, with the least amount of primitive operations. So the best case is what is the fastest way, what is the least amount of primitive operations, essentially. So in this case, you would definitely have 2. There's no doubt about that. So we have 2 primitive operations, and we have definitely n times this loop, and we're always going to check. So you have n elements at least, but then, you know, all the elements are odd, because this would be the best case, because you don't have to do these 2 operations then. So you would just have 2 plus n. This would be the best case runtime. You would have 2 plus n primitive operations. Whereas the worst case would be all the elements are even. So every time I'm going to enter the if statement, and the worst case would then be, of course, 2 plus 3n, because every time it would go into this loop and execute 3 statements here. So essentially it would have 3 primitive, let's shift this to the left a little bit, 3 primitive operations n times. So 2 plus 3n. And now it comes to the average case. What is the average case? It's very hard to define the average case, which is also why it's not really used very often, because the average case needs a very accurate distribution of elements. And if we don't know that on average, or if we know, for example, that the list elements are going to be random, we can say, okay, it's going to be probably 50-50. So half the time you're going to enter the if statement, half the time you're going to not enter the if statement. And then we could say, okay, half of the time you're going to execute 3 primitive operations, and the other half of the time you're going to execute just 1 primitive operation per iteration. So you could say, if you know the distribution or the probability of the element being even or odd in the list, you can do that. But most of the time we're not going to use the average case, because the average case is not realistic unless you really know how your data is structured. So most of the time in algorithms, when we talk about the efficiency of algorithms, when we talk about the analysis of runtime complexity, we're always going to look at the worst case. The worst case is what we're interested in, because we want to know how bad can it get if we really screw up the data, if we really screw up the instance of the problem. So some sorting algorithms, of course, if you give them a sorted list, they're done. So they need, I don't know, n operations to check if the list is sorted, but that's essentially it. We don't need anything else. Whereas if it's unsorted, it's going to take n squared primitive operations. And the best case, of course, it could be interesting, but most of the time we're really interested in the worst case, because that is what tells us how bad the algorithm can get in the worst case. That's essentially it. So last but not least, let's talk about asymptotic growth, because that's the last piece of the puzzle that's missing. And this concept is essentially saying that we're not interested in small numbers, we're not interested in constants, we're interested in what's happening in the long run. So let's say we have a function depending on n, so we have f of n, and this function essentially tells us how many primitive operations do we need to perform to solve the problem or to execute the algorithm. So in the example we just had, this would be 2 plus 3n in the worst case. So this would be the function. And what we can do with these functions is we can plot them. So we can go ahead and plot a coordinate system. I'm not going to do this professionally. I'm going to make an extra video where I'm going to do this in a mathematical program. There we're going to look at all the different runtime complexities like n squared, log n, and 2 to the power of n or something like that. But essentially, you can plot all these functions, and these functions are just the runtime complexities, the runtime of the algorithms, the amount of primitive operations, independence of n. So in this case, let's just pick a different function here. Let's delete this. Let's say we pick a constant function, so a function that does not depend on n or doesn't have n as a factor. So we could say something like 10,000, which is a pretty big number, so 10,000 primitive operations. And then we would have something like g of n, and g of n would be, I don't know, 2n, for example. And now what we do is we plot these functions. So f of n would be a straight line at 10,000, at y equals 10,000 constantly. So something like that. And then we would say, here is the point 10,000. And 2 of n would be a linear function. So essentially we would, let's get the red color here. We just have a straight line that looks somewhat like that. And as you can see, what you can see here is in the first, actually 5,000, in the first 5,000 n's, for the first 5,000 values that we can input into the function here, we're going to see the blue function dominating the red function. So you could say 10,000 is bigger than 2n as long as n is less than 5,000. Obviously, because when you have 2 times 5,000, you get to 10,000, and then it's no longer dominating it. But up until this point right here, the blue function is dominating the red function. But from this point onwards, there's not a single point where this is going to happen again. And this is the concept of asymptotic growth, essentially, because we're not interested in what's happening up until a certain point. We're interested in what's happening forever. So this number doesn't have to be 5,000. It could be 50,000. It could be 5 million, 500,000. It could be 5 million. It could be 5 trillion. Whatever it is, we don't care as long as there exists a point from which on this is never going to happen again. So when we're talking about which algorithm is more efficient, we're not looking at what's happening for a very long time. We're looking at what's happening forever, because no matter how big this number is, this span here, this range here is finite. It's a finite amount of values that we have. And for this time period here, for these inputs, okay, one function is dominating another one. But in the long run, we can see that once we reach that point, once we reach that intersection, it's never going to be the same again. So we can say in general, 2n is dominating. This is the sign for dominating. 2n is dominating 10,000. And it's actually dominating any number that you can come up with, any constant, because eventually n is going to reach half of that. So n is eventually going to reach this number divided by 2, and from this point on, 2n is going to dominate this number. So this is of course not only true for 2n and a constant, or n and a constant, this is also true for quadratic functions and for exponential functions. So the general principle here is that we do not care about the first couple of values, even if there are a trillion values. We don't care about finite amount of values. We care about what's happening in the long run. So if I have something like 3000n here, and let's say 0.1 n squared, let's plot these functions here. I could say I have a very steep line like that. This would be 3000n. And then I have a very flat curve, which is 0.1 n squared, something like that. Doesn't matter what this looks like. Doesn't matter how flat this one is and how steep this one is. Somewhere eventually we could go up here somewhere in a very long time. Somewhere these two lines are going to intersect, and you will see that the blue line is going to be below the red line eventually. I'm going to show you that in a separate video. One of the next videos is going to be about that. I'm going to show you the different runtime complexities, and it doesn't matter how long the blue function is going to dominate the red function here. All of this doesn't matter because there's some point somewhere here or somewhere even farther to the right where the red function is going to dominate the blue function forever. So you could say 0.1 n squared is dominating 3000n, which is actually not a good thing because it means that when we have a large enough input size, n squared or 0.1 n squared is going to be less efficient than 3000n. So this is very important. We don't care about small numbers. We don't care about constants because the general fact is n squared is dominating n. And it doesn't matter if you add something to it, if you say, okay, but what if I say times 5,000? What if I add a million here? What happens then? It doesn't matter. So when we're looking at asymptotic growth, when we're analyzing the efficiency of algorithms, we don't care about constants that we add. We don't care about constant factors. We care about the essential stuff like n squared dominates n, and that's enough already. So we don't care about anything else. We care about what's happening forever. And this is the concept of asymptotic growth. So that's it for today's episode. I hope you enjoyed it and I hope you learned something. It was a very theoretical one. It was a very active one. We did a lot of stuff. We analyzed actual algorithms. We talked about primitive operations, about runtime, about the limitations of certain models, about the model that we're using here, why we're using it. And there was a lot of stuff to learn in this video, and make sure you really internalize the knowledge because the future episodes are going to build on top of that knowledge. So what we learned today is very important because it's going to reoccur in future episodes. And in the next couple of episodes, for example, we're going to talk about big O notation, limiting functions, dominating functions. We're going to visualize some of the most important runtime complexities or asymptotic functions like n squared, log n log n, exponential growth. We're going to talk about all these things, and you need to have in mind that constants do not matter, that we're caring about what's happening in the long run. We don't care about small values. You need to keep in mind that we're talking about a single CPU. all the data being in a RAM. Just know all the things that you learned today, because they're going to be important to understand future concepts when we analyze algorithms and you end up with an algorithm that has a runtime complexity of, I don't know, 2000 n, and you need to understand that it's still better than 0.1 n squared. So these are things that you need to internalize, because we're going to need them in the future episodes as well. Other than that, thank you very much for watching. If you have any questions, ask in the comment section down below. Hit the like button to show me that you like the series and you want to see more future videos. And also hit the subscribe button if you haven't subscribed to this channel yet to see more future videos for free. Other than that, thank you very much for watching. See you in the next video, and bye.